Hello and welcome back again. So now you've seen an example of a complex design, and you might be asking the question, how did you decide what goes into which module? In the motion estimator, we took a fairly natural approach to the partitioning. We had two different data path elements, the PE, which was repeated, and the comparator, which wasn't. So we put those separate modules. Then we made a third module for the controller. Frankly, if you follow this approach, you might end up with a fairly natural partitioning that will be fairly straightforward to handle and lead quick synthesis runs. However, there are some general rules that do lead to better hierarchies if you follow them than if you don't. What I'm going to do in this module is give you what those rules are, explain why they're important, and then show you how if you break those rules, how you can go and fix the problem during the synthesis run, at least within Synopsys. By doing this, either writing the modules so as to be good synthesis targets, or if you have to, fixing them in the synthesis run, you will end up with quicker synthesis runs and smaller, faster designs. So just to remind you about how hierarchy is specified in Synopsys and Verilog. Here we have a module top where we instance two chiplets in it. Chiplet is a term for a further collection of modules, and they have different instance names. Here's the hierarchy within one of those chiplets. Just to keep this simple, I just cleanly separated the data path from the controller and again gave them different instance names. Because the instances are referred to hierarchically, I can call this U1 while also calling this chiplet U1. Because if I was actually referring to this data unit instance from the module top, I would actually refer to it as U1.U1, and that's fine. Here's an illustration of what this looks like pictorially with a few comments in it. Again, we have this module top. We instance in it an instance of chiplet 1, which we call U1, and an instance of chiplet 2. Within chiplet 1, we instance the controller, calling it U2, data unit calling it U1. These are the ports of each unit. The signal names, so the outputs of modules, have to be a type wire or try. And I remind you, you only want logic within the leaf modules, not above the leaf modules. For example, this gate here, in the context of chiplet 1, but not in its leaf modules, should not be done. Though if you do it, I will show you how to fix this later. So again, I remind you, use what are fairly natural partitions in general and you'll be okay. However, there's a general rule and some specific rules to follow that lead to better partitions than if you don't follow them. The first of these is to keep your modules relatively modest in size. Synopsys actually recommends a few thousand gates. This translates into basically a few pages, only a handful of pages of Verilog. You don't want one massive module to be your entire design. First of all, it makes it harder for the human who has to design and maintain it. Secondly, it leads to longer synthesis runs. The reason for this is the synthesis run is roughly proportional to the exponential or the number of connected gates that are being optimized. Thus, if you have a highly interconnected design, two 1000 gate modules will tend to synthesize in about half the time as one 2000 gate module because of this exponential relationship. So you want your synthesized units, which are either modules or collections of modules, or can even be parts of modules. There are ways of referring to the interior modules that I'm not going to go through. You want these synthesized units to be sort of small, medium in size, equivalent to a few thousand gates, in order to have them each be synthesized fairly rapidly. However, what's much more important is to make sure you follow these constraints when building your synthesized units, which are generally your modules. You want your critical path be contained within one module. This is very valuable to do. You'll end up with a lot better timing and a lot smaller design if you do this. You want every path from the input to output for that module to pass through a register. If you don't do this, you'll get unconstrained timing errors, which you'll have to go in and fix by hand, which is very tedious. You want potentially shareable resources to be actually within one procedural block or continuous assignment statement, so the automatic resource sharing can give you a smaller design. I'll give you an example of this on the next page. If you're going to apply different synthesis strategies to different modules, for example, if you're going to run the finite state machine optimization processes on your finite state machines, you want these to be in different modules. In general, it's a good idea to put your controller in a separate module anyway for each controller. Much as practical, you want one clock for each module, or at the most two, because inter-clock crossings have to be managed by hand, and this can get quite tedious if you have a lot of clocks and a lot of mixing of the clocks within a module. If it fits in with your timing plan, try to put registered outputs on your designs, particularly if you're communicating with someone else's design. This just makes critical paths a little cleaner to optimize because they're going to be entirely contained within one unit, and it makes interfacing other people's designs relatively straightforward, because in our case it makes the standard script that I've given you be the default script. Of course, I remind you, if you as a human know a better way to structure the detailed logic of something, then specify that, even if it's more code. And we've seen examples of this as we've gone along. I remind you very emphatically, all logic must be in the ESO models, even if it means you have to make a copy of a module and rewrite it just a little bit to insert that one logic gate. This is much better than putting glue logic above the leaf cell level. But all in all, keep in mind you want your design to be human readable and understandable. This leads to modules that are 2, 3, 4 pages of code typically, though that's not a hard rule, and leads to modules that map onto a few thousand logic gates. And again, I remind you, these timing ones are very important. Critical paths within one module. Every module must have a register somewhere between all the inputs and all the outputs. I'm going to talk about shareable resources. Here's a simple example. We have an if statement with 2 adds specified in it. Because you'll never have to do these 2 adds at the same time, you want this to be built as one adder and one multiplexer on the second input to that adder, rather than having as 2 adders and a mux on the output. If you write it like this within one procedural block, you will get that. If you write these as separate procedural blocks, or here separate continuous assignment statements, you most probably won't get that. The shareable resources code within the synthesis tool won't identify this as a shareable resource and go ahead and share it as appropriate. So here I'm going to have a simplified bad partitioning example, not really bad but suboptimal, and show you how to fix it within the synthesis run. What we have here is a large module foo, and this size is fine. Instance is U1. 2 modules bar, instance separately, one is U2 and one is U3. Module nip implemented as U5. Module fluff instance is U4. You'll notice a few things here. Here we have logic that's split between 2 modules. This is not that uncommon, but again, if this is the critical path, this would not be optimal. But nonetheless, we still have to somehow manage the timing interface between these modules. I'm going to show you how to do that. You'll notice that instance U3 of bar does not have this split, this logic here that's slowing it down. Normally, in a synthesis run, you synthesize each module once, and if it's repeated, you just copy that synthesized netlist. In this example, that might be suboptimal because this ALU in U2 has to run faster than this ALU in U3. And in general, faster logic is bigger logic. So you might be better off synthesizing these separately so as to get smaller logic for U3 while achieving the higher speed needed for U2. U5 has a problem. It has unconstrained paths. There's no registers between input and output. Next page, I'm going to summarize this in words so you didn't have to note it down. Again, U1 to U2, we have logic split between them. We have to manage that somehow. U2 and U3 are different instances of the same module, but U2 is to run faster than U3. And there's potential for U3 to be smaller than U2. U4 doesn't have a problem, whereas U5 has no flip-flops, so it's unconstrained timing paths from input to output. This is in words how we're going to fix these issues, at least within the synthesis run. U1 and U2. We could rewrite these as one combined module that would add an additional module to our module count and would certainly handle this if it was a critical path. We could also group them. I'll talk about the group command in a moment, so I'm not going to do that here. What I'm going to show you here is how to manage the timing when it's split like this. And then you'd only do that if it was not a critical path, and that's actually what I'm going to assume in the synthesis run on the next page. U2 and U3, I'm better off if I synthesize these separately as if they were different modules rather than the same module. U4 and U5, the only way to solve the problem with U5 is to group it with U4 and run that as one synthesis run. This will mean we won't have unconstrained timing paths. So this is how we do this. After we've specified all our constraints and set the max area to 0, instead of just running compile, we're going to hand manage the compile process for this particular example. Here I'm introducing you to the characterize-constraints command. What this does is look at the instance of a module and look around it to work out what the input delay and output delay, what the driving cell and the load cell should be for that module when it's synthesized. And this will work all this out for you, so you don't have to go through and specify it by hand. So here what we're doing is running characterized constraints on U1, which you recall, I'll just use this, is this big module here. So what we're doing here is calculating what output delay we need due to the delay here. But no, U2 hasn't been optimized yet, so this actually might be quite large. We'll come back to that. We then set current design to be that module. We compile just that module. We go back up the hierarchy, current design to top. Now I'm going to fix the problem that we want to group U4 and U5 together so that U5 doesn't have unconstrained paths. The way we do that is with the group command. We just group U4 and U5 together, give it a new design name, in this case pets, give it a new cell name, in this case U10. We then characterize that as one new module in a sense, set the current design to that, pets is what we called it, and compile just that module group. We then pop back up to the top design, the top module. Now what we're going to do is fix the problem that because U2 and U3 have different interface timing constraints, we want to synthesize them as if they were two different designs, not the one module bar. We do that by creating a new module within the synthesis structure by this uniquify command. We're going to run uniquify on cell U3, give that a new name, bar 2. We now synthesize U2 and U3 separately. First I'm doing this for U2, characterize constraints, current design bar, compile, go back to top, characterize constraints U3, current design bar 2, this new temporary module name that we just made, compile that, go back to the top. We've now finished our hand managed synthesis run and we do a timing report at the top level. That is important. We don't want to accidentally do the timing report at the leaf cells. That won't catch everything. Now, just a few questions on this. Think about this. Is the area of the logic in a shared timing path from U1 to U2 optimal? That is this area here. The answer is no. When we ran characterized constraints on foo, we hadn't done any synthesis. Thus, this module here was unoptimized. Thus, this delay here, which became the output delay of that pin there, is very long. We really want to go back and run this again now that we've optimized U2. So what I'm saying here is not necessarily optimized, because when U1 was synthesized, the U2 logic was unoptimized. We could fix that by just running it again. Run characterize on U1 and a compile incremental on U1. Remember, all compiles for the modules after the initial compile have to be incremental. Going to remind you, why should every path be in a synthesized unit contain a register, which we fix now, so we don't get unconstrained timing paths. And particularly if you're dealing with other designers, it might be valuable to consider registering your outputs so that set input delay and so on can just come from the standard script. But it's not necessary to do that. You can still manage this by communicating that the standard script no longer applies, and thus working out what numbers should be given to a neighboring designer in order to cope with a different design. Now, there we hand managed the design because the hierarchy that was specified by the designer was less than perfect. If you have a perfect hierarchy, it is much simpler to do your design, and this is what you should aim to do in your project. And that is quite simple. Current design to top, compile. What this actually does is automatically do a characterize and compile for each module within the design. And again, this only works if you don't have glue logic above the leaf cell level. And I'll show you how to fix that in a moment. So here was an example of a good partitioning. We had a motion estimator. We had a very natural human readable partition. The PE, which was instanced 16 times, comparator, which is instanced once, the other unit in the data path, and separately the controller. Remember, design the data path before the controller tends to lead to the controller being in a separate module. We group these together in top without mem for synthesis purposes, because this is the hierarchy we're synthesizing. This was then instanced in top, where we also instance the SRAMs. We don't want to synthesize the SRAMs. If you accidentally do this, your synthesis runs will get very, very long as it tries to build these massive register file arrays. The SRAMs do not come from the synthesis tools. They are predefined blocks that are incorporated into your design. So in this example, the motion estimator, the synthesis was straightforward. Current design is top without mem, compile. And what this actually does is run characterized constraints on the I/O of each of the modules and compiles those modules. Then assembles a hierarchical netlist, including the fact that PE is replicated 16 times, and that becomes the final design. Here's an exercise. Let's say this was a critical path between U1 and U2. This is less than desirable. It is not going to be easy to optimize that critical path if you're synthesizing foo and bar at the same time and separate synthesis runs within the same tool run. You have to fix this. You could either combine the modules by rewriting them, or you could do this. Current design equals top, assuming these were instance and top. Ungroup dash all dash flatten, compile. Ungroup dash all dash flatten just takes a hammer and flattens out all the hierarchy. The other place you might use ungroup dash all dash flatten is when you have design where within a module and replace dash synthetic doesn't work, which occasionally it doesn't for some reason. Here I have another example of a bad design that could be fixed in a similar fashion. Here I have a module foo, which has two modules in it. a bar instance as U1, snafu instance at U2, and then we have one AND gate above the leaf cell level. We have glue logic above the leaf modules. If you have this, again, the only way to fix it is with this big hammer. Current design equals foo, ungroup -all just flatten, and compile that. Of course, what you're doing is leading to a longer synthesis run because you're synthesizing this as one Uber module. But it still might be quicker than rewriting the modules. So that brings us to the end of this particular instructional module. I remind you, in general, you want to partition the design into modestly sized modules, a few pages of code, a few thousand gates. And it's important to make sure that each module, that the critical paths are contained within one module, that from all inputs to all outputs of a module there is at least one flip-flop. You want shareable logic between one module, in fact within one procedural block. You don't want logic gates above the leaf module level, but nonetheless make your design sensible and human readable. I thank you very much for your attention in this module. The next modules we're going to look at some other issues related to design before actually turning to the non-design portion of this class. Thank you very much.